I wanted to hear more about these T-brains you were going.
Well, I went to my office, but to discuss the question that you asked about FI and masses together.
Okay, let's start our afternoon session. It's my pleasure to introduce Erich. Most of you maybe don't know that Erich is probably the most responsible for this conference because he wrote my first recommendation letter for my first postdoc. Which is the only postdoc I got, so and I'm pretty sure he was responsible for me being here. So thank you, Erich, for this lovely workshop.
Thank you guys for inviting me. I want to publicly apologize to the speaker this morning. I took a nighttime flu pill. I've been a bit congested here last night, and I woke up at 1. Okay, that's huge. I don't know what happened. I missed the alarm. So anyway,
Is the mic on?
Oh no, no. So this is not for the record. Okay. So no, it's not. So this paper is about quite an old subject, but there are some new twists in it. And because this is a rather diverse audience, I thought I should start the crash course on N=1 coordinate super mills. This is a gauge, which is what most of the talk is about. This is a gauge theory in 4 dimensions. The gauge group is SU1. Apart from the gauge field, there is a gaugino field, which is an adjoint fermion. It has a discrete chiral symmetry, which is Z2n. And there is this gaugino bilinear, which is gauge invariant, and it gets an expectation value which brings the symmetry to Z2, and the same vector. And one of the most interesting things about this relation is exact. This is a very rare occurrence in 4-dimensional quantum field theory, that you can have an exact relation. This quantity, which is a non-perturbative quantity, is expressed in terms of a strong coupling scale, which is defined really in one loop perturbation theory. Okay? And this relation has been checked in many different ways. 2 of them I will mention. The third is Simon Newton. This is why I wrote this list here. Okay? And so this is the situation before 2010. It was known also before 2010 that this theory, in addition to the zero form discrete chiral symmetry, has a 1-form chiral symmetry. And somehow important implications of that were missed. Okay? And this is what this talk is about. The motivation for this work, the title that I really will mostly discuss is this. It sounds like a mindful when it's also 70 pages long. Okay? Unnecessarily so. But I should also say Adi is coming. He's hearing this for the 3rd time. Okay? Condolences, but hopefully there is some twist and something is explained better. There's also other people who heard it before. Okay? In different locations. So in any case, let me explain the motivation. The motivation, one of them I said, there is these generalized symmetries. The world changed in 2014, at least for the high energy people, that there are new generalized symmetries with new anomalies, etc. And introducing 2-form backgrounds for this 1-form center symmetry can lead to a fractional topological charge. And that is related to my other motivation, which is classical studies of confinement. And these studies are able to show in a controlled way the relevance of fractional objects of fractional topological charge for confinement and chiral symmetry breaking, advocated by many, including Gonzalez Arroyo, whose name will appear later. But taking some partial compactification of 4-dimensional space, such that you take R2 cross T2 or R3 cross S1, you find in a very controlled semi-classical way that this is the case, that these objects contribute to chiral symmetry breaking, as in this theory, or to confinement. And for me, I cannot do any justice discussing this. For me, it is important that in this situation, R3 cross S1, it provides one of the 2 weakly coupled calculations of the gaugino condensate. And it has a continuous connection to R4, and it's one of the checks on this exact relation. And there is a long history of work. The 2 calculations are using SQCD on R4 and then taking a limit to large mass. That happened largely in the 1980s and a little bit in the 1990s. And in 1999, there is also a Durham connection, Valle Jose, who lives in a different world now. So anyway, he's not here, but he's at Durham in a different department of it. Valle Jose was involved in that. And aspects of this calculation were not finished until 2014, believe it or not. So in any case, there are these 2 things. And I want to do the following thing. I want to revisit something that was done 30 years ago. The thing that was done 30 years ago by Cohen and Gomez first, and then Schiffman and Weinstein also wrote about it, is to do a calculation of the gaugino condensate on T4 with appropriately twisted boundary conditions. And the exact result on R4 is given by this expression, 16 pi squared. squared lambda cubed in some definition of lambda. The coefficient depends on pi by lambda. Okay? The old calculation gives this answer with some constant c, which was left hanging. Okay? And I want to revisit this because we have a much better understanding of the physics on T4, the Hilbert space on T3 with a twisted set. And the questions we want to address is how well we understand semi-classics in the femto universe. The femto universe is an approach to non-perturbative gauge theory pioneered by Belka. When you take the gauge theory compactified on a very small space, the space is smaller than the size of the strong dropping scale, so you can use weak coupling methods to calculate in principle everything. And of course, how that is related to the infinite volume limit is anybody's guess. Okay? But in any case, these things exist, and there has been recent developments, and so we want to know how well we understand semi-classics. Is there continuity to the infinite volume limit, in particular here testing the condensate, and of course, what fluctuations contribute to the region of condensate. So these are my goals, and we'll see that there are some puzzles studying, and maybe some people will find something interesting to contribute here, more mathematical than I, as I will mention at the end. Okay? So the main player for me will be the theory quantized in a canonical formalism at first. When you have the theory of torus, then you have three center symmetries, one in each direction. The center symmetry for me, the one that's important is in the three directions, so I call the corresponding operator T3. It generates the center. Oh, I'm talking about SU2, sorry. I'm trying to make people happy to finish, so in time, so I'm talking fast, okay? So T3 generates the Z2 center symmetry, and now I commute with the Wilson loops in the three direction, okay? And because it's a Z2 symmetry, it has eigenvalues labeled by mod 2 integers, so the eigenvalues are plus or minus 1. The Hilbert space, because T3 is a symmetry, splits into flux sectors in the third direction. They're labeled by E30 or E31 in SU2. And you can think of these so-called flux sectors heuristically in the following way, already discussed by Kuft, is that you can go from one sector to Hilbert space to the other by taking a winding Wilson loop and applying it to the corresponding state in Hilbert space. Of course, I just warn you that this changes the energy. This is not some weird theory where the Wilson loop generates a symmetry. It's a kind of a normal theory. But it takes you from this sector to this sector in Hilbert space. So this is my main setup. And in addition to that, I will have a special proof twist in the 1-2 plane. For the young people, what that means is that I take a background for the two-form Zn gauge field, gauging the one-form center symmetry, which you're all familiar with, and I make this integral be non-zero in every 1-2 plane. Okay? So this is how I consider my theory. And then there is something remarkable in this theory. The mixed center chiral anomaly that Zohar and company discovered in Hilbert space in this background has a very interesting representation. It leads to a center deformation of the algebra. X is the generator of the Z4 chiral symmetry, and the anomaly, once you introduce this background and 1-2, leads to the fact that the two symmetries, the Z2 symmetry generated by T3 and the Z4 symmetry generated by X, don't commute. And you have two symmetries that don't commute. They commute with the Hamiltonian. This means that there is a double degeneracy of the spectrum. And what the chiral generator does is this changes, it takes you from one flux sector to another flux sector. So the entire Hilbert space on a torus in this background is doubly degenerate. It's a very rare thing in quantum field theory that that would be the case. It's an exact statement. Okay, there is no tunneling should cancel. Okay? So this is my setup. And it's important to realize that if you take the infinite volume limit, these two, the lowest energy flux states, which are degenerate, should become the two clustering vacua in the infinite volume limit. And these are the two vacua which are interchanged by the spontaneously broken chiral symmetry from the anomaly. Okay? I say this because very smart people last time I was giving this talk were raising questions about this. This twisted boundary condition should be relevant in a gap theory, such as this theory in the infinite volume limits. Okay? So that's a sort of a general belief. There is also evidence. People studied, Tepper and collaborators, studied lattice pure angles in a box, with or without twists, and they were looking at string tensions and glue balls, and they found that if the box is large enough, if there is twist or no twist, it doesn't matter. These quantities are the same in the two theories. So this is some evidence according to this claim. Another comment is about the realization of center symmetry. So if I consider the correlator of two Wilson loops in the third direction, so in the direction orthogonal to the plane of the twist, so I take one here and one here, so they are located somewhere in the 1-2 plane, and I take T to infinity. And when I take T to infinity, this projects, of course, on the ground state, and I'm looking at the expectation value of some ground state. And this now is an exact statement in this limit T goes to infinity. This W only only has non-diagonal matrix elements between the two ground states, so this goes from one state to the other. So this correlator is equal to the square of the matrix elements of the Wilson loop between these two flux ground states. And in general, that's non-zero if you keep the sides of the torus finite. But if you take L2 to infinity, the plane where the Wilson loop is located, then by clustering you expect that this matrix goes to zero, and you get area law and unbroken center symmetry. Okay. So the quantity I'm interested in is this gaugino bilinear that I wrote here, and I'll be calculating the following thing. I will trace over this Hilbert space with a twist, and I'll be doing, of course, a supersymmetric calculation, so it's a twisted partition function. I'll be calculating the expectation value of the Wilson loop of this condensate, and there'll be an insertion of the center symmetry generator in the tree direction. And written in terms of the states in Hilbert space, this is the sum over all energy eigenstates. Of course, they are degenerate. There is a sum over the degenerate flux states. The T3 eigenvalue gives a minus sign if the flux is 1, and there is this expectation value of the gaugino condensate. And the remarkable thing is that when you calculate this quantity, the gaugino condensate has opposite expectation values in these two flux states, and so this product is the same for the two flux centers. This is because of the computation relation with x and y. Okay. So what this expectation value is really calculated is twice the trace, this weighted by e to the minus beta and minus 1 to the f of the gaugino condensate in one of the flux centers of Hilbert space. Okay, so this is the quantity I'll be interested in. And I will normalize by path integral without lambda squared and without 3. And this path integral is just the Witten index, which is equal to 2. Okay, so in other words, I'll cancel the factor. So this is what I'll be calculating using the Hilbert space technology. In terms of the path integral, this is the following thing. So I realize this is a little fast, but my point is this. My point is that I have an insertion of T3 in the top, in the numerator, and then in the denominator. Inserting T3 in the numerator twists the boundary condition in the time direction, and it means that there is a twist in the 3-4 plane, where 4 is the time direction. And what this means for the path integral is that you're summing over topological charges which are z plus 1/2. Okay? So that just you have to denote that. In the denominator, I'm summing over topological charges which are integer. And this path integral is what I will be computing, assuming the torus is small, so I take the limit of the Femto universe. I expect semi-classics, the sum over classical saddle points, to be a good approximation in that limit. And I can get the result for this quantity. And in the numerator, of course, the leading contribution will come from topological charge 1/2. And in fact, it will be the only contribution. It will have precisely 2 zero logs by the index theorem. I will discuss the calculation, but let me first talk a little bit about the big picture. So we're calculating this quantity, and having this expression, we can now take limits. If I take beta to infinity, this means only e equals 0 contribute. And then if I take L1 to 3 to infinity, then I obtain an expression for the R4 gaugino condensate, okay, which is what people have calculated earlier.
Great question.
Yeah.
Does this tell you about the gaugino condensate without minus 1 to the f? Can you say anything about that?
Yes, in the limit beta goes to infinity.
In the limit beta goes to infinity, yes.
Because there's just one state.
Yeah.
I see. And the results you wrote here was that limit. It was beta and e. Yeah.
These calculations were done with the infinite value limit.
Yes.
I mean, but it's supposed to be at least naively independent of beta.
Sorry?
It's supposed to be independent of beta because of supersymmetric
Well, this
cancellation.
is what we'll talk about now.
Not the one without the minus 1 to the f. You're saying the one with minus 1 to the f.
The one with minus 1 to the f is supposed to just give you the ground state contribution, which is the infinite, and because energy is 0.
So this would be the case if we had an exact answer for this quantity, okay, which we believe the calculation at every data and L1, 3, etc. What we're going to do is we're going to do a semi-classical calculation in the limit of the Femto universe, and this calculation by itself involves some assumptions which will be stated later. But I will argue, as Tim was suggesting, is that this result is actually independent of the size of the torus and also of the coupling apart from the dependence of the strong coupling tail. So we'll come to this in the end, but I want to flesh out the important salient points about the calculation because I think there is something to understand there. Okay, and as I said, the leading semi-classical contribution comes from several points with topological charge 1/2. And the natural question that arises, what are these instantons? And who wrote a paper in 1981 called Some Twisted Self-Dual Solutions for the Yang-Mills Equations of Hypertones. So I'm referring to this paper not because of these SU2 solutions, which are remarkably simple, but because of this SUN generalization. As a motivation for writing the paper, he said that considering how difficult it was to find, it was worth publishing. Okay? So for a truth paper, this has remarkably few citations. For many of us, it would be great, but for this, not so much. Okay? But the solutions I'll be considering here, because I'm doing SU2, are based on this solution. This solution is a very simple solution. I will not go through showing you this satisfies the appropriate boundary condition, but it does. Okay, so it's a Abelian solution. It's in the tau 3 direction. It's really a constant magnetic field, if you want to call it that. And there are some moduli which are also lines in the 4 directions that will play an important role in what follows. And the field strength of this solution is really given by this expression, as everybody can check by comparing the two sides. And this solution is self-dual, or BPS, if the two sides of the torus are symmetric. Then F and F2 are the same. Okay? So, it's important, this BPS condition is important because it assures that one has the minimum of the action for the given topological charge. It preserves one half supersymmetry. It preserves one half supersymmetry, and all kinds of determinants cancel up to a power of the polygon house. Okay, so this is wonderful. And one can attempt to use this solution and work in the limit of symmetric torus, and then everything goes pretty bad. The reason is that once you study this solution, you find that there are 4 undotted and 2 dotted zero modes, which of course is consistent with the index theorem, but it means that this background is not completely consistent because these zero modes source the gauge field equations of motion. They should be lifted, but we don't understand how. And of course, also this symmetric limit does not allow taking some interesting limit, but maybe for now this is not so important. I should say that Cohen and Gomez used this solution, they called it tori back then, presumably unaware of the solution question. Okay, I don't know. Okay? And in any case, in 1984, the Hilbert space interpretation of on T3 with the twist was not understood, so interpretation of the result would have been difficult. Gonzalez Arroyo and his collaborators, they devised a way to deform the symmetric T4. So depart from this limit and impose the BPS condition. And if you do, I will not discuss the details. If you do that, then you find that there are only 2 undotted zero modes, precisely what you need. There is no source term in the equation of motion. And of course, you depart from this symmetric torus condition, so it seems good. So all of this sounds fantastic, but there is some bad news. And the bad news is that this deformed solution analytically is only known to leading order in a parameter which measures the deviation for the symmetric torus. For SU2, there is numerical evidence for uniqueness and convergence upon comparing to the numerical solution for rather large values of delta. So we'll stick with that. And now I want to make an important remark because I think this is where some progress can be made, presumably by a careful analytical analysis. If one knew general statements about the modular space of solutions on a torus with topological charge R over n, I'm departing SU2 now, one could do certain calculations in super Yang-Mills theory only using this knowledge, not the explicit form of the solution. One would need the metric on the modular space and its volume. And because some correlators just used to that. But this information is not known. So we proceed with trial and error, okay, and that's what we did. As I'll discuss, our result may be taken to suggest that this is where likely some progress will be made. And just to show you a picture from our last paper, when you go to order delta, to leading order in delta, when you deviate from this condition, the solution becomes non-abelian and it acquires X dependence. And this is just some fun plot just to show you that well, this is a solution for charge 3 over n in SUN bigger than 3. There are 3 lumps, there are moduli, etc. It's a very interesting thing, which I will not talk about.
Sorry,
yeah.
I missed why do you care about this non-symmetric limit?
The main reason was to have a background where I don't have the extra zero modes.
Okay. Because you have these 2 undotted.
Yeah, exactly. So this was the main reason. So deforming the symmetric torus and working to leading order in delta, we find that there are only 2 zero modes. There are no line bar zero modes. There are 4 translational moduli. We have some explicit expression, it's also important. Both the measure and the condensate are independent of this parameter to all orders. And this assumes, of course, convergence, and it uses supersymmetry. So supersymmetry is given. This is supersymmetric background. The convergence, of course, we base our relief on the numerical evidence. And to give you a flavor, it's usually supersymmetric theory. If you integrate over the moduli of trace lambda lambda, you find that if this P equals 1 half background, or in any instant on background, this integral is actually proportional to the classical action of the solution. And it follows from supersymmetry. The zero modes are related to the classical solution. And then this classical action to all orders in delta is just 1/2 the instanton action. Okay, so this is where we use supersymmetry and and the most important thing, I think, is to figure out the range of the moduli. And how do we figure that out, absent general mathematical statement? Well, we require, we use some consistency condition. So I can consider the same Fento universe and the same twisted partition function in Yang-Mills theory. And in Yang-Mills theory, we know that the expectation value of the Wilson loop has to vanish in this background. And the reason is that if I calculate the trace, the Wilson loop has no diagonal elements between the flux factors. Okay, this is very well known that the Wilson loop in finite volume vanishes, but this is sort of a formal justification. So what we demand is we take pure Yang-Mills theory in the same small box, and we calculate the twisted partition function. So the leading contribution is from Q equals 1/2. There is no Q integer. There is no Q equals 0. This is the smallest action. So and we demand that this winding Wilson loop, when you integrate over the moduli, because this is the instanton contribution to this quantity modulo determinants, etc., you get 0. And this requires, let me skip the details in order to finish. This requires that this moduli Z vary from 0 to 4 pi. And this range of moduli, which is found by demanding that the vanishing the Wilson loop vanishes, is consistent with the fact that there exists gauge invariants, which evaluated in the solution take different values when Z goes beyond 0 to 2 pi. The reason I'm stressing this so much is that this range of Z of the moduli from 0 to 4 pi means that the instanton wraps around twice in every direction of the torus. Okay, it's what it says. So local gauge invariance identifies Z with Z plus 2 pi that corresponds to going once around the torus, but the one dressed by the Wilson loop see the difference. So it seems that consistency and uniqueness of this fellow point require us to assume this. And so this is the most important ingredient in our result. And once the dust settles, this is what we obtain. Remember, this is the quantity we calculate. All the qualifications are stated on the right-hand side. We have Hilbert space with the twist. We have a finite volume. We have some ratio, etc., etc. Okay? And collecting everything, we find a result which is exactly twice as big as what people found on using these other calculations. And so this creates a little bit of a puzzle. This creates a puzzle because I argued that, or I will argue, that you expect that this quantity does not depend on the details on L4 and also on L1, L2, and L3. And so I want to argue that this result is independent of the size and also independent of the coupling up to this dependence that enters the line scales.
Isn't that the same size and coupling? The
Sorry?
coupling is set by the circle.
There could be additional dependence on the sides. There could be dependence on L times lambda due to some leading corrections. So it turns out that the usual argument for holomorphy that people use on R4, it also holds on T4. The usual argument is that you take a derivative with respect to the log of lambda star, where lambda star is the anti-holomorphic scale, and then you find that this brings down F star, which is the thing that lambda star comes from, and this is some supersymmetry transformation of something. And you use supersymmetry and supersymmetry of the vacuum on R4 to argue that this vanishes. This argument actually calls on T3 as well. And on T3, you just need to argue that the sum of our states of a given energy and a given flux of this quantity is 0. And in this one can explicitly check that, knowing that the states form representation of the supersymmetry object. So this argument of holomorphy says that lambda squared is some constant times lambda cubed, and it's not allowed to have L times lambda dependence. It would mean higher order corrections. You know, this is really and this argument appears known to Shipman and Weinstein, who without derivations, they just mentioned it should be dependent on the size. Holomorphy leaves open dependence on other ratios, or dimensionless ratios of size like delta, but they seem not to occur. So we seem to have a problem, and this is my message apart from the last slide. It seems that we could have made an algebraic mistake. We have spelled all factors in lower detail in the paper, even though the 70 pages symmetries, checking those factors is very straightforward. A lot of the paper contains checking properties of the solutions in the delta expansions, which are not so relevant. Okay, so getting to the factor of 2 is pretty easy. There could be a loophole in the L independence argument. I don't see in the moment. To me, the most likely culprits are the last two. We could have misidentified the region of integration of the module. There could be some global identifications that we're not aware of, and we need a rationale for that. And the reason I'm stressing that compared to my previous talks is that we recently discussed these solutions of charge R over N in SUN, and then we find explicitly there's some very intricate identifications between modules. And we don't understand them, okay, mind you, they're not in the paper, we just construct the solution. They're intricate identifications, and there could be some here that we're just not smart enough to figure out. It could be that other backgrounds contribute, but given the numerical evidence, it's very unlikely. To boot, using one of the two SUN solutions, the one he considered difficult to find and wrote his paper about, we found that for SUN we have n times this result, okay? It's very interesting. Okay, the usual normalization. So this is it. Okay, what did I tell you? I tell you that recent advances in understanding generalized symmetries, anomalies, etc., has led us to be able to revisit an old calculation of the gaugino condensate, which is a rather fundamental quantity in this supersymmetric Yang-Mills series. And we calculated it on T4 in this paper, and it has been calculated in R4, and we obtained this result. And understanding that is important, okay, to be better human beings. I don't know. To understand better semi-classics in the Pental universe, it means that something is missing in our understanding, okay? People are pushing adiabatic continuity from R3 cross S1 to R4, etc., etc. So if we can understand that, we can understand anything, because this is something which is very highly controlled by symmetry. So in the future, we wish for a better understanding of fractional charge instantons, semi-classics, and their role in gauge dynamics. So this is just a general thing. But there's something very concrete that the math, physics, and string community could possibly contribute. You know, just occurred to me preparing my talk. Very general statements about the instantons follow very naturally from D-branes. For example, the ADHM construction is most simply, most intuitively explained by thinking about P minus 4 branes inside P branes. And of course, this is done on S4 or R4, I'm not sure. I think it's one of them. And similarly, actually relatedly, fractionalization of DPST instantons on the column branch is also understood in terms of D-branes. And the Nairn transform is just the T-duality of this system, okay, which relates some different modular spaces. So what I'm wondering if it's possible to to revisit these things on T4 with twisted boundary conditions. So you only need to add the two form background. And I asked Miyaki yesterday, he said it was difficult, okay? But, well, it's a challenge, okay? That's my story.
Okay. Do you have questions for Eric?
Yes. This lambda here, which is a counterpart of lambda QCT for this supersymmetric theory.
It's the whole one term. It's the whole.
Yeah, could you explain more about it? Because I think lambda QCT, we don't have a explicit formula for it, right? But so
this is a one loop scale. So
it is one loop.
it's one loop, yes.
It's one loop exact, or it is one loop.
It's one loop exact.
Okay.
Yeah, the holomorphic gauge coupling, when the super-Yang-Mills theory is regulated in a certain way, only runs at one loop, and this is the associated Stokes scale.
I think so.
Okay, that's
But
it's
this
a
is
long song and dance, okay?
some particular screen.
Oh, absolutely, yes. Yeah.
I think that
He's hearing it for the
third time.
okay.
So
Are you going to ask the same question?
I hope not. But I think that T4 cannot be a real result for T4. There must be a bug. And the reason is the domain walls. If you have a factor of n discrepancy at large n, it means that the domain wall tension that you will calculate, that results from that has a discrepancy of n. You will get that the domain wall is like n times heavier. Now the domain wall, we know it's like a D-brane. It has to scale like n, not n squared. So what I'm saying is that even on T4, it cannot be a real result for T4. One may think, okay, it depends on the topology and there is some subtle things, but I think that even on T4, you have a factor of n, a real problem somewhere.
I know we have a problem.
Yeah, that's it.
models that you think would contribute?
I have no clue actually.
So if you take one of these top instances,
These are the full tests. This is what we
yeah,
use.
if you take one of them, it gives you n times.
Yeah. But we are taking one of them, and we are. You see, again, the reason I went into so much, I didn't go into detail, but the reason I spent time on this is that, you know, this factor of 2, when in SUN the factor of n, is tied as to what is the range of this moduli. And I told you that what we are finding here is physically, it means that this instanton wraps force around the torus. So the instanton lives in a, not a bubble, but I guess 16-fold cover of the torus. And there could be some discrete identifications, and I cannot wrap my head around it. Okay, so I think the question of the module and the solution is interesting.
Could you just impose that it's 2 pi instead of 4 pi?
If you impose 2 pi, then you get an inconsistent result.
Okay.
Then you get the Wilson of non-zero. If there was a reason why there was a global identification, reflecting all the z's to minus z's, for some reason, that would get a factor of 1/2, but I have no good reason for that.
Yeah, maybe related question. Does the global structure of the gauge group affect this periodicity? The range of, I didn't
Well,
get what the
gauge
z's
group is
are.
SU1.
So.
The gauge group is SU1.
But with backgrounds.
With a background for no one for service.
But are Wilson loops then even, they have to be connected to some surface in the presence of these backgrounds?
In a sense, yes. This is why the, yeah, it's true. Yes. But the fact that they have to vanish is true, okay? This is a statement which there's no doubt about.
I asked you this question previously. I mean, there's an effective theory for R3 cross S1, which is exact. Did you try to put these backgrounds on this to this effective theory and compactify in the effective theory?
But there's no relation to this calculation.
No, but I mean, you can check whether I mean, you should get that it does not depend on the size of the torus, at least if the torus is big enough. And
Look,
that would be some consistency check.
On R3 process 1 in the infinite R3 the configurations that contribute to monopole instantons.
Right, but put them now on T3 cross.
So this is an unsolved problem.
Yeah.
Because they have long range fields and you have to
No,
absorb them.
but you have an effective theory, which is in terms of cosine sigma, you know, this whatever. You have the B and the sigma field, and so in the effective theory, put the background for one. Don't do microscopics.
It's,
You should be able to do that.
we can talk about it.
Yeah, we have any more questions? I'm a very bad chairman.
I have a dumb question. It would be natural if we were just summing over all n ground states somehow when comparing to the 4D results in actual fact.
But I spent quite a bit of time.
I know, but it went very fast.
Okay. But this is very simple.
No, he meant it in private.
No. This was the story. So we have, here is SU2. So we have 2 flux sectors. This is the exact degenerate sectors in any finite size torus with the 2 twist. And the point is that the algebra, the anomaly algebra, implies that the value of the gaugino condensate in the 2 flux sectors is opposite. And because I'm twisting with -1 to the 3, which is the T3 eigenvalue, this quantity is the same in the 2 vacuum.
But aren't you summing them?
Sorry?
No,
I am saying no, but they're equal, but the contributions are equal. So the sum over E3 equals 0 and 1 can be replaced by a sum over E3 equals 0, which is just one of the sectors of Hilbert space, times a factor of 2. This is what I did from going to here to here. Yeah, it was fast, but
And when SUN is somehow
it's
cleaner,
absolutely the same. Yeah.
SUN is cleaner because this factor
You get a factor of n.
and it's a factor.
Yeah.
You just delete that factor of n.
No, but this factor we deleted. We cancelled the denominators. So there is an extra factor of n. Okay, that's the whole point.
so this is in addition.
In addition,
This is the naive.
this too is cancelled by the Witten index, yes. I'm sorry, this is too fast. David Tom, come on. You can take it.
Okay, any more questions?
Okay.
If not, let's thank Erich one more time.